So continuing our discussion about efficiently computing recursive functions, let's look at the problem of computing grid paths. So we have a grid, a rectangular grid, where we start walking at the bottom left corner. And the rule is that we can only go up or right. So we want to start at the bottom and we want to reach the top right corner. So we can number the coordinates. So the bottom right corner we call 0, 0. This particular grid has got 5 columns and 10 rows. So the top right corner is 5, 10. Right? And the question that we ask is how many different ways are there to go from 0, 0 to 5, 10. So what do we mean by different ways? Well, here for instance is one grid path. This blue line takes us up from 0, 0, then right, then up, then right, and so on. So this traces out one particular sequence of edges along this grid, taking us from the bottom left corner to the top right. So we could of course choose a different one, which in this particular one, the red one and the blue one are completely disjoint. They don't use any of the same edges. But in general, I could have paths which overlap with other ones. So this yellow one partly overlaps with the blue in the middle over here, right? And then it overlaps with the red one over here, right? So we want to know how many such different paths are there from 0, 0 to mn. Now it turns out that this problem is actually a very classical problem in combinatorics, counting, right? So the way to analyze this is to see that if I want to go from the bottom to the top, then I must in one dimension I must go from 0 to 5, in the other dimension I must go to 0 to 10. So totally I must make 15 steps, right? There is no choice, I must walk 15 segments. In general, if I am going to some m comma n, I must walk m plus n segments. Now if I have these 15 segments and I am going to 5, 10, that means I have to go right 5 times, right? And I have to go up 10 times. Now in which sequence I do these rights and ups is what determines which path I take, right? But every path will have exactly 5 right moves and exactly 10 up moves, right? So there will be 10 up moves and 5 right moves. So now if I take this and I think of this as an overall thing saying this is my first move, this is my second move, this is my third move and so on up to my 15th move. Then if I tell you that you moved right, I moved right at these positions, at some 5 positions, then automatically I must have moved up at the remaining positions because I have to do exactly 5 and exactly 5 right and 10 up. Okay. So therefore, all I need to do to determine exactly which path I am taking is to fix the position of the 5 right moves among the total 15. Right? So among 15 positions, I choose 5. Okay, this is usually written as 15 choose 5. Right? So this is a very standard combinatorial thing. 15 choose 5, n choose k is n factorial divided by k factorial into n minus k factorial. Right? So 15 factorial divided by 10 factorial times 5 factorial. It happens to be 3003 in this case. So for this particular grid, there are 3003 ways. Now of course, instead of choosing the right positions, I could also have told you the 10 positions where I moved up. Okay, that leaves 5 open positions where I must move in right. Okay, so this would give us 15 choose 10. And so it's not a coincidence that 15 choose 10 and 15 choose 5 are in fact the same expression. Okay, so whether you choose to compute it as 15 choose 5 or 15 choose 10, it doesn't matter. So in general, it's going to be m plus n choose m or m plus n choose n, where I'm going from 0, 0 up to m comma n. Okay? I have to make m right moves and n up moves. So I need to choose m out of m plus n total moves or n out of m plus n. Both of them will give me the same expression because that's why n choose k is n factorial, k factorial, n minus k. So if you just exchange k and n minus k, you get the same expression. So that's all very well. But what, for example, if this was not a perfect grid? Supposing we have some intersections which are blocked. So in this particular case, if we look at this intersection, which is 2, 4, right? It's 1, 2, and then 1, 2, 3, 4. So we have put a black mark to indicate that for the moment you cannot go through it. Right? So any path that goes through 2, 4 should not be counted among the valid paths from 0, 0 to 5, 10. So the blue path that we had drawn before actually goes through this intersection. So this path is no longer a valid path. The red path is okay because it bypasses it, but the yellow path unfortunately also goes through this intersection. So of the three paths that we had seen so far, two actually don't go through. So the question now is, out of those 3003 paths that we said were there from 00 to 510, how many of them are still valid if we are not allowed to go through this intersection? So it turns out that actually this also has a combinatorial solution. So what you can say is that in order to go from here, and if I want to avoid a blocked intersection, so let me see how many ways are there of going through it and just remove them. Right? So what I will do is I will say that every path that goes through the current blocked intersection is a path from 00 to 24 followed by a path from 24 to 510 because it goes through 24. So we can think of this as a smaller grid from 00 to 24. Right? So if we solve this, this is the general m plus n choose n. Right? So I get 6 choose 2. So I get there are 15 ways to go from 00 to 24. Likewise, if I consider this grid, okay, then this is 3, okay, and this is 6. Because it was 10 and 5, I've done 2 and 4 respectively. So after 2, there's still 3 left horizontally. After 4, there's still 6 left vertically. So this is like going from a new 00 to 3, 6. Okay? So there I get 6 plus 3 choose 3, and this turns out to be 84. Now any path which comes to the bottom to 24 followed by any path that goes from there to the top is a valid path passing through 24. So I have to multiply these two numbers. I have to take 15 times 84 and I get 1260. So this is the total number of paths which are going through 24. But I don't want paths going through 24. I am saying that paths going through 24 are not allowed. So I must count all these paths as invalid. So I take the original 3003, subtract, so I take 3003 and I subtract 1260 and I get 1740. Right? So taking our combinatorial exercise to the next step, I can find out how many paths go from the origin to a given point on the top right, provided one position is blocked. So this imperfection could be more complex. I could have two positions blocked. Right? In this case, the blue, yellow and red paths are all invalid because the red path also happens to get blocked. So now I have a block at 2, 4 and also at 4, 4. Okay? So if I count all the paths going through 2, 4 which I have already done, I can subtract those. Similarly, I can compute all the paths going through 4, 4 and subtract those. But now what happens is that this yellow path, okay, is subtracted twice because it is part of the paths going through 2, 4 and part of the paths going through 4, 4. Right? So I have accidentally removed it twice from my total. So I have to put it back. Right? So you have to now compute those paths which go through both the intersections and add them back. So this in combinatorics is called inclusion and exclusion. You come across it also sometimes when you do Venn diagrams, when you do sets. If you want to find out, you say how many sets have one element, how many sets are the intersection, how many sets. So you have students taking 3 subjects, English, history and physics, and then so many take English and history, so many take history and physics and so on. So when you do that kind of counting, you do exactly this inclusion exclusion. Right? So as we get more and more messy grids, this combinatorial question becomes more and more complicated to solve this way. So let's look for a better solution. So as you might guess, since we are looking at these kind of inductive formulations and recursive programs, what we are really looking for is an inductive formulation of the grid problem. So let's ask ourselves the following question. How do I get to a point ij on the grid? So I claim that given our structure, which is that we can go right or we can go up, there are only 2 ways I can come here. I can either come right from a neighbor on my left. So from ij minus 1, I can make one step right and come to ij. Or from I minus 1j, I can go up one step. So if I have any path which starts at 0, 0, right? Any path which somehow comes to ij minus 1, then by taking exactly one step, that path becomes one path to ij. right? So every path from 0, 0 to ij minus 1 can be extended in a unique way to ij. Likewise, any path which comes from 0, 0 to I minus 1j can be extended in a unique way, right? So if I count the paths coming to the two neighbors, then each of those paths can be extended to reach the current node. So therefore, I get an inductive formulation as follows. So let's write paths ij to denote the number of paths from 0, 0 to the current point ij. So what we have just seen from our inductive analysis of the problem is that if we are at ij, then the paths come from the left or from below. So the paths to ij are the sum of the paths to I minus 1j and the paths to ij minus 1. So there are of course some boundary conditions. So if we look at our grid in general, then if we look at the leftmost column, or let's start at the bottom row. So we start with bottom row, right? Then we know that this is of the form 0, 0, then 1, 0 and so on up to 5, comma 0, right? So anything of the form I0 derives its value only from the left because there is no corresponding move from below. Similarly, if I am the leftmost column, then this is 0, 0, 0, 1 and so on up to 0, comma 15. And now there is nothing from the left, so I can only get it from j minus 1 from the row below. Okay? And finally, we have to ask ourselves what happens at the initial condition. So if I am at 0, 0 and I want to go to 0, 0, how many ways are there? Well, this is a trivial path. There is only one way by just staying there. It's important that it's not 0 because remember that if it's 0, then everywhere you're just adding things and nothing will come. You'll get no paths. Okay? So it's important that there is exactly one path from 0, 0 to itself. So how do we deal with holes in this setup? That's easy. We just say that whenever there is a hole at a given point, we just declare paths of ij to be 0. In other words, if there is a hole at some point, okay, then this thing is going to contribute 0 regardless of what's above or below. So if I have something coming from here and here, I'll just ignore it and say this is 0. And likewise, when I compute the thing above, there will be some value x coming from the left, so this will just be x plus 0. And similarly over here, there will be something coming from below, say y, and this will be 0 plus y. Right? So any hole will just have by declaration, okay, paths ij equal to 0 because nothing can go through it, and this will automatically propagate to its neighbors correctly. The remaining inductive definition is exactly as before, right? So if it's not a hole, it depends on its two neighbors. And then we have the bottom row left column and the origin as base cases. So the difficulty with this calculation is the same as it was with Fibonacci, which is that if I have a particular calculation, so for example, supposing we start our recursive calculation at 5, 10, okay, then this will ask for 4, 10 and 5, 9. Now these in turn will both ask for 4, 9. So 4, 9, if I just evaluate this paths function recursively the way it is written in the inductive definition, it will end up calling paths of 4, 9 at least twice from this perspective, and this wasteful recomputation will occur throughout and we will get an exponential number of calls to paths. So we have seen before we have two technologies to deal with this. So one is memoization, where we just make sure that we never call paths ij with the same value of I and j more than once. The other way is to anticipate the subproblems, figure out how they depend on each other, and then solve them directly, iteratively in a suitable order. And this is what we call dynamic programming. So how would we use dynamic programming on the grid? So this is our grid with the two holes at 2, 4 and 4, 4. The first thing is to identify the DAG structure of the dependencies. Right? So we know that every ij depends on its left and bottom neighbor. So this is how we do the DAG, if you remember. If this depends on the two values left and below, we draw an edge from the left to this node and from below to this node. So this is the DAG structure, right? So the yellow edges represent the DAG structure. So the DAG structure goes naturally from the bottom left to the top right. So this is the only 0 in degree node in this DAG. So if you want to do a computation of this grid, the grid paths directly using dynamic programming, the only place we can start is 0, 0. Right? So we start at 0, 0 and we fill the value there, which is 1. And now we observe that we have two possibilities. We can go to the right or we can go up because these two dependencies are now removed. So let's just go row by row. So if we do this value, then automatically this dependency will go, so we'll be able to do this value, then this will go, so we can do this value, and so on. So we can compute the entire bottom row, and these are all inherited from the left using our base case, right? So, and it's very clear, I mean intuitively it's clear, there's only one way to get to any of these places, which is just to go straight from left to right, okay? No deviations possible. So there's only one path to every node on the bottom row. Now we can move up one row, and we can see that this node in the first row or the second row is now available, it was already available. But if we do that, we can also do the node to its right and the node to its right and so on, right? So we can fill the entire second row, and at each point we are just adding up. So 2 is 2 plus 1 plus 1 is 2, 1 plus 3 is 4 and so on. Likewise, we can do the next row. So for example, 6 plus 4 is 10 and so on. Likewise, we can do the next row. 20 plus 15 is 35. Now we come to the holes, right? So at the holes we said that these will be 0 regardless of what comes from below. Even though there's 10 coming from below, this first hole must be 0. With 35 from below, this hole is 0. Right? So we just compute this row exactly as before, except at the holes we put a 0 regardless of what is coming into it. We don't count it as 5 plus 10, we just put 0. We don't count this hole as 20 plus 35, we put 0. Now when we go to the next row, likewise, this 0 contributes only 0. So above it, because no paths can come through this direction, the number of paths coming here is only 6 coming from the left. Similarly, the number of paths coming here is only 26 coming from the left. Okay? Similarly, the number of paths which are coming to this point, okay, could not come from there, so this 20 is copied there, this 56 is copied here. So we can do this row by row, and if you can just enumerate every row like this by copying, adding up the values to the left and below, and we'll find that there are actually 1363 paths with these two obstructions. Okay? And if we move the obstructions around, we can redo this calculation. It will be as efficient. We don't have to worry about this inclusion and exclusion. So this is one way to do the dynamic programming, but remember any topological sort will work. So we could instead start with one and go column by column. So we can go up and fill that, and then we can fill up the entire first column. The first column will again be only once because there is only one way to do this. Having filled the first column, now we can fill the second column, and then we can fill the third column and the fourth column and so on. And obviously this is only a different way of enumerating the values don't change. So we should eventually end up with the same values at every point. And finally, you can also do it by diagonal. So notice that when I do this one, then these 2 points now are 0 in degree nodes. So I can do both of them. Now I have these 3 points as 0 in degree nodes, so I can do all 3 of these. Then I have these 4 points as 0 in degree nodes, so I can do all of these, and so on. Okay, so this is just to emphasize that the choice of topological sort is entirely up to you. Very often it will be more complicated to program this kind of diagonal thing, so usually one tries to do it by row and column, but any topological ordering of the base values can be used in order to compute them. All you need to know is when you come to a node, a value that you want to compute, all its dependencies must have already been computed. That's what this DAG structure gives you. Right? So the subproblems form a DAG, and you have to navigate your way through the DAG in the most effective way as far as programming it. It's usually by row or column in a table, but it could be by diagonal also. So finally, before we conclude, let's just look at an instructive illustration of the difference between memoization and dynamic programming. Okay, so if we have a bunch of holes which are along the border, then intuitively what it says is that if I start from here and I go anywhere like this, I'm going to get stuck. Okay? So if I start my memoization from there, then everywhere is just going to see a 0. Okay, so all these values are just going to be 0, and my memoization is not going to look further along these. So memoization, I claim, is only going to look along this outer boundary. Only these grid points will actually be computed by memoization. Okay. Whereas if I do dynamic programming, I will start from here and I will blindly fill up. Only when I reach the 0, I realize that the values are computed inside this grid, don't fill up. Right? So there is this entire shaded region in this grid whose values are not needed because they cannot contribute to any path from the bottom to the top, because every path going through them will get blocked by one of these holes. Right? Whereas dynamic programming is now going to blindly compute values for these points even though they are useless. Memoization will not, because it only computes by need and it will never reach these points. So therefore the memo table will have a linear number of entries, right? It will have, say, 2m plus 2n entries. It will only have the outer outer boundary of this grid will be covered. So it will have a linear number of entries in terms of the two dimensions, whereas dynamic programming will have m times n entries. It will have every grid point will be computed in the table, even though most of them are useless. So in a sense, in this example, dynamic programming is wastefully computing values which we can, by a little bit of uh, analysis, realize will never be used, because it is just blindly computing every subproblem on its way from the origin to the top. However, as we said before, dynamic programming is iterative. It is going to be just a simple loop. Memoization is going to be recursive. It is going to be optimized to not make the same recursive call twice, but nevertheless it is recursive, and recursion carries a cost in terms of execution in a programming language. So therefore, though this looks like a wasteful dynamic programming strategy in case the holes are distributed in a bad way, actually it doesn't matter. It usually turns out that a dynamic programming implementation will be usually more efficient than a memoized implementation. So the memoized implementation is easy to do because we know that we can go from an inductive definition directly to a recursive program. And we saw last time that there is a generic formula or a recipe to make any recursive program memoized. You just have to insert a couple of steps saying look up the table and feed the table. Right? So therefore getting a memoized implementation is very easy. Getting a dynamic programming implementation requires some analysis of the subproblems and figuring out a good order in which to evaluate the subproblem. So it is more work. But this extra work usually pays off because then you get an iterative computation of all the subproblems rather than a recursive one.